on Monday. Any doubt questions you have, like anything? I mean, you felt that yes, I was able to make that inverter, I was not able to make the inverter, anything like this? No? Anything you can type, or you can come on the voice and let me know. Am I audible? Need an memory? Shall I switch it to my hotspot? Yes, kids, you have to give me some hint, some cue on this. Something you have to write. Am I audible to everyone? Let's start with this. The most asked question in these times. I just changing my Wi-Fi network. So just give me a moment in case the connection loosens up. Just give me a moment. Okay, I'm here. Sorry. Okay. Yes, you will get the recording, dear. No problem. I will ask the team to get the recording of the last lecture. In the meanwhile, if you have any doubts of the assignment that we did on Monday, I gave you, I asked you to design a basic inverter. And I think we have already done that, right? Then I asked you to make an inverter and put some load on it. And then I asked you to increase this load in the third assignment, that design an inverter for to invert 100 megahertz signal, which can drive a load of 0.5 picofarad with less than 150 picosecond of rise and fall time. Where were you able to do this, everyone? How was this experiment? You can come on the voice, that is more faster. Okay, let me try making this for you by sharing my screen. Can anyone let me know who's the host right now? Nihal. Hi, Nihal. Can you make me host, please? Nihal, you can just open the participants window and select my name and click on more and just say make host. As my connection was dropped, so you were made host by default. Thank you. Thank you very much. Okay. So I just share my screen. Okay, I hope no one is in the waiting room. I believe all are inside the meeting. Okay. So let's say if I asked that day to make inverter. So let me make an inverter for you guys. So let's go with the default values of MICROWIND. I just generate an NMOS and click again MOS generator, generate a PMOS. So it shows 0.086 milliampere. I align it on top of each other. I zoom it. Then from the palette, I select the metal one layer and short these two nodes. I take the tin gate, short these two nodes. Then I take a VDD for the PMOS one side terminal, take a VDD for the N well, ground for the NMOS one terminal. Then I take a square clock, apply to this input. Now, as I wanted 100 megahertz, right? So I want 5 nanosecond high and 5 nanosecond low. That will make 10 nanosecond, that will make 100 megahertz of frequency bandwidth. Now I take a visible node and connect to the output. Then we wanted a load of 0.5 picofarad. So I take a virtual capacitor and make it 0.5 picofarad. I just change the color and simulate and give him some time to run. That is for around 10 nanoseconds or maybe 20. Did you also got such kind of response, and were you be able to solve this problem? Yes or no? Yes, kids, let me know. Did you solve this? You can see that this guy is not inverting properly. The rise and fall time are in the order of 3 nanosecond rise time and around 1 nanosecond fall time, which is way beyond my expectations. Okay, I asked you to make it 150 picosecond, right? So how many of you were able to do this? Right, this was the assignment. How many of you were able to do this? Okay, if you like WhatsApp chat, that's okay. I mean, sorry, normal chats, we can talk over the chat, or you can come over the audio and talk about it. Am I audible? I believe I asked you a simple question. To let me know. Should I just turn off the slide at the back? Huh? Okay. Getting different output. Okay, you can even copy paste your simulation results over here, isn't it? Anyone? How did you got it? Like, can you share? Anyone can share me your hello, guys. You have to participate. You have to let me know about what you think. Can you please talk about it? Yes, Nihal, can you share your screen at least? Guys, am I audible? You have to participate. Okay, you can just copy paste your design. You can't change the properties of transistor after placing it. You have to design it. I mean, like, you have to redesign it. Okay, let's do one thing. Instead of putting too much of time onto this question, let me know how many of you solved this or attempted this experiment. How many of you attempted this experiment? Okay. Okay. A couple of people coming up. Okay, no problem, Rafael. No problem. Okay, let's do one thing. I do this for you, and then we will repeat it. Okay, I will give you 5 minutes of time period. Okay, which you have to follow through. Okay, so let me share the screen back again. So first of all, you have to do the math. Obviously, the math comes first. That it is like that you are making an inverter, okay, and there is a load which is a 0.5 picofarad, okay, and now obviously we know that the time constant is some dependent on the RC factor, okay. So C is constant, which is assumed that it is 0.5 picofarad. Now what is that R? Okay, so R is nothing but the resistance of this guy. Okay, the resistance of this guy. So resistance means that how much amount of current he can pull from the VDD and inject inside this capacitor. Okay. So assuming that you have to do this math, okay. So you want this as 100 picoseconds, okay. So R is constant and C is 0.5 picofarad. So you get some RQ value, okay. Maybe I just open this calculator. 0.5 picofarad. It would be somewhere around 0.2 ohms, I believe. Okay, something like this, I believe so. So, or even less than 0.2 ohms. Okay. Then you have to do a reverse calculation and find out V is equal to IR, that at this particular voltage, etc., that how much amount of current is required to be injected, okay, to get the resistance. Let's say you do some math, obviously, and you have to find out that this is around 5 milliampere of current is required to achieve that factor, or maybe 4.5 milliampere of current is required to achieve that factor, little bit low, okay. So you need transistors of these current drive capacity to inject through it. So I just open my MOS generator. Okay. So as I want higher current, so obviously the width is higher. The width is much more higher. Okay. So as we know that the current is proportional to W by L ratios. So this width has to be increased. Okay. So I just mentioned the micrometer length as maybe 10. Now that's looking too high. 5, no. Yeah. So around at 5 micrometer, I will get around 4.5 milliampere of current. That's good. So I just place it on the clipboard. Okay. And this is how you see your NMOS transistor look like. Okay, so this is a simple your NMOS transistor. You can see that this is the same length. Okay, the length is same. Length is length is equal to 2 lambda only. Okay, and 1 lambda is equal to half, or you can say the technology divided by 2. Okay, as of now your length is equal to 45 nanometer. Okay, but here you look at the width. This is your width. This is your entirely completely the vertical side is the width of the transistor. More the width, more the current. Simple as that. It's just like, you know, a pipe can deliver more water if the diameter is larger. That's it. Okay, larger the diameter, more the current can pass through. Okay. Now I need a PMOS. I need its companion. Now the PMOS also should have equal. See, being equal is important. Okay, it has to be equal. So my PMOS is 2.6 milliampere for the same width. See, this is important. For the same width, it is giving a little less current, but that is a phenomenon we are aware of, and that's what we have seen in the last lecture. If you have doubts, we can talk about it. No problem. So this width will not enough. I may give him 7, no, 9, a little bit over, 8.5 maybe. Yeah. So for 8.5 micrometer, I get 4.56 milliamperes. So that's great. So I just place it on the clipboard. And you can see this guy has a little longer width as compared to the NMOS. So that's fair enough. Okay, I just zoom to this area. I hope you guys are not following. Okay, don't follow it. Just have a look on the software. Keep your eyes open. Just understand it, because you must have observed the software is not difficult to learn. You will follow it. Don't worry. I will give you time to do that. Okay. So I take a metal one and short these two ends. So that makes my output. I take the tin gate and just short the gates. That's it. This is done. Now take a ground, connect to the NMOS terminal, VDD for the N well, and VDD for the PMOS, the other terminal. You have to just hover on top of the node and just place it. Then take a square clock, apply the gate. The time low would be 5, time high is 5. And this is the node I want to see. And as promised, we will put a load of virtual capacitor of 0.5 picofarad. That's it. Change the color for better visual and simulate it. Voila. So you get rise and fall delay of the same order 1 and less than 100 as we planned for. We wanted less than 150, it's 1/3. So probably the current 3 milliampere would have been good enough. 3.5 milliampere would have been good enough. Okay. Now put questions. Shall I ask you guys to follow the same to same? Because this is what I want you guys to practice more and more hands-on and do the same. Okay. Okay. Then is everyone ready with your mouse, keyboard, monitor, and the laptop? Is everyone ready? Okay, so this time we will do follow through. I hope everyone is watching and listening. Why 5 for the clock? Oh, Rafael. Good. No problem, Rafael. I think you that's a good question to ask. And it's always good to ask anything, huh? Except who killed whom, I don't know. rest of the technical grounds on this software you can ask. Okay, so when you open the cloud, okay, so this part of the software that helps you to apply various kind of inputs. So this is your time low and time high. So the description of the waveform is applied here. We want a 100 megahertz clock, right? So this is the frequency. The reciprocal of this will come as 10 nanosecond. So 10 nanosecond is one clock period. So this is 10 nanosecond. Okay, so this is on for 5 nanosecond and off for 5 nanosecond. Hence 5 nanosecond low, 5 nanosecond high. Okay, you can even mention the rise and fall time. For example, you want some waveform which is like this and like this. So that also is possible. You can just specify that rise time is 1 nanosecond, the on time is 4 nanosecond, and the off time is, like the fall time is very less, something like 0.01 or 0.001 nanosecond, something like this you can specify. So this is to just to apply various inputs to the inverter. Okay. So let's do a follow through. You can start up your softwares. Okay. You can just start the software fresh, keep it in the 45 nanometer technology, and we'll make it right over here. And then I will also keep on answering your questions and the doubts which can be popped up in your head. Ready? Okay. Go to MOS generator. Select the NMOS in case your NMOS must be by default should be selected. Make the width as 5 micrometer. Okay, or maybe 3 micrometer. Let's put it 3 micrometer, please. Let's everyone keep 3 micrometer. Okay, done. Can one guy can be an mic lock by replying yes or no? Any one of you, maybe Rafael, as he was the last guy to answer.
Yes, sir.
Okay, now click on MOS generator again, select PMOS. Now we want the same current to be of the PMOS. So it is 2.7. So I just make it around 4.5, 4.6, 7, 8, maybe 5. Yep. So by default, Likhit, right, Srikar, by default, the software should open in 45 nanometer. By default, it is 45 nanometer, and we will work in the default technology. I will let you know how to change technology, but maybe tomorrow, next class. Okay. So for the PMOS, select 5.1 micrometer as the width, and then just say generate device and place on the clipboard. Okay. So if you just view all, this is how your both NMOS and PMOS should look like. Is it okay?
Yes, sir.
Great, thank you. You know, if someone can be prompt reply so that I can catch up. The more faster I get, and more coverage of the grounds we do. Now on the palette, click on the tin gate. Just click once on the tin gate, and now you're able to draw. So just draw a block and short both the gates of the transistors. Then select the metal one, left click once on the metal one, and short this node. Make this node and short the NMOS and PMOS both sides. Okay, so once this is done, we're ready to simulate. So select ground and connect to the NMOS other side of the terminal. So this will become ground or the VSS. Now select the VDD, select VDD, don't select VDD high voltage or VDDH. So there is a higher voltage and the output will be not right in that case. And put it on the anvil, the green net kind of block what you see on the left hand side. Then select VDD again and place it on the PMOS, the other side of the terminal. Okay, now Puja, undo is only once, not much, because generally the layout softwares don't encourage undo functions. Okay, because something goes wrong, that is not visually possible to verify it. Okay, and there are some more reasons to it. Okay, so in case something goes wrong, you might have to delete that part of the layout, understand it, how to join it. Okay, now take a square clock, left click on the clock, which is on the palette over here, and place on the red body, which is the gate input. Make this guy as 5 nanosecond low and 5 nanosecond high. Make sure it is only the low and high part, not the rise and fall time. Assign it. Now from the palette, you see a last symbol, which is of eye looking symbol. So just left click on that visible node and place it on the output. You can call it, if you want, you can rename it or let it be the default value, which is S1. Okay. Now take a virtual capacitor and place on the output and make this guy as 0.5 picofarad. Okay. I just changed my color. If you want, you can press Ctrl W to change the color background. If not, then let it be on the default colors of the black background. Up to you. So this comes well. Now I will wait for few notifications from your side about the work done. And once I get that, yes, everyone has done this, we'll proceed to the next logic. I keep my part of the window zoomed over here so that if anyone wants to reposition himself. I'm available over here, right in front. Graph scale. Which graph scale, Nihal? You can click on zoom all in that case. Graph scale. You mean this screen? You can change the time scale to around 20 nanosecond is good enough to see your 2, 3, 4 outputs. Okay. Simulation graph, which one? Like voltage versus current or voltage versus time? Maybe you can come on audio, that will be more faster. Okay. In that, there's a time scale. You mean time scale? You can just drop down the time scale and select whatever you wish to go for, 20, 50, 100, 500, like that. Okay. Anyone else? How about others? How is it going? Are you able to do this? Can I have a couple of feedbacks? Good, got me. Okay. Okay. Now let's do one thing. I just saved this file on my folder. Okay, and see it again. I just remove the folder, create the folder. VAC is on the palette there. It is called as ground. I mean, it looks like the international ground symbol. How about others? Are you guys, see guys, you have to let me know, was it done or not? Okay, good, Prithvi. Good, Yashwani. Okay, good. Chalo, let's take the next concept on the software, which is very simple. And I give you another assignment. And let's move ahead. Oh, okay, sorry. I should have explained one thing. Okay. Did you guys notice that this transistor is too big? I mean, the height is too long. Okay. Now, there is also one concept which is like of the real estate. Anyone in the real estate? Anyone here? Anyone would like has some spare money to invest in some plots, etc., or flats even will do. Anyone here? Rafael. Oh, good, yeah. Okay. Chalo. Let me pitch my plot to Rafael. Rafael, I have a plot for sale. Okay. And the dimension of the plot is this, like it is 100 feet by 10 feet. Will you buy it? Someone has an audio on. Come and check. Hello. Okay. I have a plot for sale. The dimension of the plot is 100 by 10 feet. Okay. Do you think that anyone will buy it? Okay. Let me have yes or no. Couple of yes or no. I will make my judgment on that. So the area is 1,000, let's say, square feet. Okay. Anyone will buy it? This 100 by 10 plot? Ouch. Why? Why? Sorry, I mean, it came somewhere. Why? Sorry, it is still new to this. Very few uses. Right. That's very right. 100 by 10 plot has, you know, the issue of aspect ratio. Okay. It has an issue of aspect ratio. Now I have another plot for sale. Okay. Okay. Which is maybe 20 by 50. Okay. So the area again is the same. Okay. The area is again same, but aspect ratio is much more better than the previous one because I can make use of this plot, which is a little bit squarish in shape. This is a little squarish. So keeping that concept in mind, look at this. Okay. These. Okay, these transistors, they are big. The width is too large. Okay, too large. So anywhere fitting of this into some layout would be very difficult because if I rotate this, it will become like this. So it will be very fit to fit. I mean, like put these transistors into any giving layout geometry. They might be possible, but then the chances are very low. Okay, as you said that the uses are very low, so it is on the possibility. So this is not a good idea to draw the single transistor with so high widths. Instead of that, what we can do is we can use fingers. Okay, so let's come back here. Just have a look and then you can follow through. Okay, so I want an transistor 2.7 milliamperes. Okay, so instead of that, I can just increase fingers. Okay, I just make 4 fingers and make the width as 1 or maybe 0.5. Yeah, around 0.75. Yeah, around at the width of 0.77 and 4 fingers, I get almost the same value of the current, which is 2.7 milliamperes. I just generate device and place on the clipboard. So he makes an transistor like this. Now remember, it is the way you make use of this transistor. So what actually he does when you say fingers? So by fingers, we do not mean finger chip, but definitely something in multiples. Okay, something like in our hands, like which are in multiple. So this how it look like, 4 fingers coming vertically upwards like that. So what he does when you say fingers, so he puts like this. Okay, so that's an NMOS, NMOS, NMOS. Okay, so hold on, let's make it over here. So let's say this is a point A and this is point B. Now, if I have to use this transistor set, this is how he generates for you. He just generates it. Now, what happens? These are the adjoining points. Okay, so these are the points at which these are already shorted internally. Okay, they are internally shorted. So you need not to waste your materials in designing extra or layout. So you see this part. Okay, so these are already done. Okay, so this is how it is. So this is your one NMOS. Okay, so you have this drain and this is the source. Okay, and in between the gate material. The second one is this one. Okay, the second one is this one. So you have drain over here and the source over here. Okay, and that's it. This is how it is. The only thing is that this thing is common to both of them. Okay, so this thing is common to both of them. So I can make use of them in series. I can make use of them in parallel. Okay. So in parallel, what I have to do? I have to just short all of them. Okay. I have to just short all the inputs. That's it. They will become in parallel. Okay. Then what? I have to short the alternate inputs. This, I will short it. This, I will short it and short it. Okay. So this will become A, maybe B, and this will become A. That's it. Okay. So over here, what is done? So MICROWIND does the layout generation for you by, you see this and this point, this and this point. Okay. So already these points are shorted. So what in MICROWIND you have to do is, this is 4 fingers. So if you short the metal lines which are coming out from the bottom side, and also if you short the metal lines which are coming out from the top and the metal lines which are coming out from the bottom, then they will become in parallel. To make in parallel, short these to make in parallel. Okay, is this good? Okay, so let's make this them in parallel and see how does it sees. So you have to click on metal 1 and draw a block like this, and draw a block on the top side. That's it, voila, it's done. And take a tin gate and maybe short on the top side. So either side, on the top or bottom or both, as you like, depends on that. Okay, so that makes an NMOS transistor which is shorted and in parallel. It's the same current carrying capacity, remember that, don't miss that point. Now I click on PMOS. So in this case, I keep the number of fingers as same. I don't increase fingers because what will happen then, there would be alignment issue. If I want, I can increase the fingers also, but I don't do that. And I change the width. I make it 1, no, 1.4, no, 3, yeah. So at around 1.3, it will have the same current as the NMOS. So I just generate device, and somewhere on the top of it, I just place it. So here I have a PMOS, which is in, I mean, like series or parallel, you decide. The current which is shown is of parallel. That is not of series. Okay, that is of parallel. Okay, so if I have to make them in parallel, the same logic. We short the metal lines which are coming out from the top side and short the metal lines which are coming out from the bottom side. That's it. And they will be in parallel. Okay, so let's do that. So I take a metal 1 line and just draw a block and short the upper side of the metal lines and short the bottom side of the metal line. At the same time, I just short these 2 nodes and bring the output a little bit outside of the ledge. Okay. Now I'm ready to apply inputs to it. So I take a VDD supply, connect to the envelope, take a VDD supply and place it on the upper side of the metal line, okay, to apply and bias VDD supply to the PMOS. Okay. Now, as this node of the NMOS is connected to the output, so I'll leave this node, but definitely I take the ground and connect to the bottom 1 metal line. I take a square clock and apply to the input red line and make this guys 5 and 5. And I take the visible node and connect to the output node. S1, I don't mind. Take a virtual capacitor, place on the output, make it 0.5 and apply. And I missed one point, that the PMOS, I didn't shorted the gates. So I take the tin gate and short them and also join with the NMOS. Okay, I can join like this, or I can make an entire block, up to me. Okay, let's simulate this. Almost same values. The current was changed in around few microamperes, so hence the delays are a little bit out of the line. But still, where, when they will overlap? Sorry, I missed the question. Can we discuss again? No, the metal and tin gate don't overlap because they are on top of each other. They are not on the same level. The floors are different. You know, one is on the ground floor, one is on the top first floor. Okay, so they do look like overlapping, but they are actually not. This area you mean, Niyal, right? So they're on top of each other. So if you see, this is a 3D view, if you have not seen earlier. So this is how the structure looks like. So these are the gate material, and the bottom one is the diffusions. And these are the gate materials which are shorted and made a box. And the metal one is on the top layer. They are not on the same layer. But as we look from the top, it looks like they are overlapping, but actually not. Okay. So in this case, now you can see that the aspect ratio is much better. Okay, the aspect, see, remember the area is not different. Okay. Can I ask a simple question? I just put the layout of what we made yesterday, just now, and just save this file as maybe 2. You can do a side-by-side comparison of both layouts. Okay. So in this case, the width was very high. In this case, the aspect ratio is okay. Okay. So this is how the difference both of the designs make. Okay. And both can drive a 0.5 picofarad of load and within rise and fall time delay of the 100 picosecond. Okay. Now, if I ask a question simple, what will be the gate capacitance of both of them? Okay. Option 1, same. Option 2, half. Option 3, it's different. What it is, we don't know, but it's different. Very less. If I ask you the gate capacitance, you understand what is gate capacitance? If you have any MOSFETs, obviously every MOSFET has a gate capacitance, which is called a CG. If I ask what will be the CG of both of these designs, how it will be? I know you guys don't know the exact value. It's very difficult. But then I'm asking an quantity analysis. Will it be the same? Will be half? Will it be different? Half is like the second one is half. Second is half. Is half. It would be different. Or the second guy would be very less. So select your options. Yeah. Can I expect some couple of answers? Mm-hmm. A little bit different. Okay. Okay. Yes, 2 answers. There are how many participants? 25 we have today, excluding couple of people, at least 20. So at least 25% should answer. At least 5 people should answer. Width is different. Okay, I got it, Nihal. Others? Rafael, did you fly out? Can you come back from Ambala? Sorry, yeah. Yes. Pooja, Yashwani, Sahana, Akshata. There's so many participants, right? And where is that my Germination guy, Rohan Reddy? I can't see his logo today. Is he absent? Only two answers. Yes, guys. Am I audible to all of you? Can anyone confirm? Okay. So yes, Pooja, what's your option is same. Okay. Sankarsan, what is your option? Select anything. Go for any bluff or a fluke, no problem. Okay, they will be different. Okay. So it's same, half, different, very less. Okay. So let me ask a non-technical question. So I have a plot 1. Okay. Whose dimension is 100 by 10. Okay. Then I have a plot second, whose dimensions are 50 by 20. Got it? Got the idea? Now I need to cover both of these plots with tiles. I have to use tiles and put finished tiles across the entire surface of the plots. How many number of tiles I will require in both cases for both plots? 1, same, half, different, or whatever option it was, very less. So it's same, right? Good. So it's same. Yep. Because the number of tiles fitting is related to area. So if area is same of both of the plot, then the number of tiles required will also be same. So if we know this, so the same logic is applied over here. Yes, this guy has a higher width, but this guy has higher number of transistors, right? The number of transistors are more. Eventually the gate capacitance will also of the same order. If it is different, it is because the exact values are not matching. It is like 100 by 10 what we said, the second guy is 50 by 20.1. That is the size of the plot. They are not exactly equal. If the dimension would have been equal, then definitely the gate capacitance will also be equal. Now in MICROWIND you can just check that by I just zoom and select double click on any of the node, so it gets highlighted and the rest of the node gets de-highlighted, and then you can just see the properties of this. So this guy mentioned the gate capacitance as 6.73 femtofarad of the left and one side inverter. Now I select the right hand side, so in this case it is 6.45. So again it is same. There is a fractional difference, but that difference is because I have not exactly made the same transistors. They were not 100% same to same figures. You remember the 2.71 and then 2.712, that was the current carrying capacity. So slightly difference was there. Minor, but then this is what the minor difference you can get seen this. Okay, so that was one concept I wanted to clear on it. Okay. So I will give you guys 5 minutes break, because that's what our religious time would be, that every hour I require 5 minutes of break. Otherwise, your neck will start paining and it will fall off from your body. Okay. So we just take a 5 minutes break. We'll come back. And in the meanwhile, I expect that everyone should be able to do this finger technique drawing by yourself. So everyone has to practice this. Okay. Chalo, see you again. Okay, I'm a long queue on the coffee machine. Hello, am I audible? Hello, guys. Yes, guys. How's it? Okay, shall we start? I believe you guys were able to replicate the same stuff. Okay, fingers. Did you? Yeah, shall I assume that this was done? Okay. Now let's progress to little more complex and a little bit more sophisticated. Okay, we will do gates. Okay, and to start with, we take a NAND gate. Okay, and NOR gate. So my today's target would be a NAND gate. Okay, and maybe NOR gate also, and we will try to do a comparative maybe in the assignment. Okay, so let's start with NAND. Okay, so a NAND gate we are familiar with, right? It's a very simple NAND gate has such kind of table that if you give any input 0 0, the output will be 1 1 0, okay, 0 1, sorry, so output will be 1, or 1 0, the output is 1, or 0 0, output is 0, right? Right or wrong? I mean, like, you guys can confirm me that no, sorry, the gullet table one adi. Isn't it? Okay. Yes. Hmm. So, in terms of schematic, how it comes? Is it like this? No? Okay. So, anyone over here who's not familiar how the NAND gate works and what's their functionality, how does they work? Anyone here, or everyone is just familiar with it? You guys can be a little bit fast in answer so that we don't miss the precious time. Am I audible to everyone? And my visibility is not so important. Okay. Mm-hmm. No? Okay. Okay, I do quickly. So in this case, what happens, like if A and B, when the 0 0, so both of the PMOS are on, okay, the output is charged to level 1, okay, to both of the PMOS, okay. And in case of 1 0 and 0 1, okay, so in that case, only one of sorry. Okay. In that case, only one of the branches charging and any one of the NMOS is off. So now as there is no direct contact with the ground, so hence it is not pulled down. So only in the case of 1, 1, in that case, both the NMOS turns on and both of the PMOS are turned off. In that case, the output goes to 0. Okay. So this makes clarity, I believe. Okay. If that makes clarity, then let me add in this. In this case, both NMOS are in series and the PMOS are in parallel. Okay. So let's make up this. Okay. But before making of this, I would like to put one more concept on the table, that something which is called as worst delay, worst case delay or propagation delay. Okay, propagation delay of the gate. So if this is the NAND gate, okay, and that was VDD, and that is the Y. So when you put the table, okay, so in this case, when only this guy is working as an inverter mode, then guy it is taken, because when both of the PMOS are charging, okay, when both of the PMOS are charging the output, okay, so we have to take the worst case delay. Okay, so either we take this one, because either one PMOS is on and another guy is off, okay, or the vice versa, that this guy is on and this guy is off. Okay, so the only one path should be selected, because when both paths are there, then they would be like there are two resistors in parallel. In that case, the resistance will become half. The resistance will become half. Okay. We will pass through this concept. So let me make this NAND gate for you, and then you guys can follow through. I believe this NAND gate is in your assignments, and it's part of your curriculum. So I go to MOS generator and change the value of number of fingers as 1, because this time, or maybe number of fingers as 2. We'll take 2 number of fingers because they require 2 transistors in pairs. Okay, and select NMOS. Then I can just say this is 10 lambda. In micrometer, it comes as 0.2. Okay, so in micrometer, it is 0.2. And generate device and place on the keyboard. I select PMOS and let it be at 0.2. So you see both PMOS and MOS will have the same width length ratios. Just keeping some space in between for routing, and I just place on top of each other. So now you can see that they are in board. And now if I apply input here and take the output here, this will become in series. Okay. But now if I give input here and short these 2 nodes, okay, and take the output from here, then they will become in parallel. Okay. Same is for upper one. Okay. If I give input over here and short these, short these 2 nodes, okay, these opposite metal lines, and take the output from here, so they will become parallel. Okay, so simple it is. So that's why we use fingers. The construction is easy, fast, and more compact. So I take the metal one. Okay, and first of all, as PMOS are in parallel, I short these 2 points. Okay, NMOS is in series. Remember that. And that is a parallel node which comes down, take a right angle, little bit extended, and one mode joining here. That's it. So I take a VDD supply, connect to the N well, VDD for the PMOS, ground other side of the terminal. Okay, then I take a square clock, apply to the input, and call this as A. Make it time low as 1, time high also 1. Then I take the square clock and connect to this point and call this as B. Now take the tin gate and short the opposite side of gates. So this NMOS, this PMOS, they are in pair. And this is the visible node. Connect to the output. I change the background color and go for simulation. Voila, it works nice. Maybe I just add a small capacitor to the output load just to have a little flavor. So I add a small 0.01 picofarad capacitor and simulate again. Okay. Now, in this case, this is 0, 0. Okay, let's leave the first shot. Let's start from somewhere over here. So here A is 0, B is 0. So this guy is 1. Okay. So 1, 0, 1, 0, 1, 1. Okay. Then 1, 1. Then it comes 0. And this is the fall time. Okay. That is the fall time we have to observe. Now, during the next transaction, this guy becomes 0. Both of the PMOS become 0. Then the output charges back to high. And at that time, we can see the rise time. And we distinctly see that both PMOS are on. So that means technically this should not be treated as the worst case delay. So to identify the worst case delay, we have to tie either of the input to VCC. So I just open this, and instead of clock, I go to VCC supply and assign it, and then simulate again. Now, in this case, what happens? You can see the B input is tied to VDD. Okay, so actually the NAND gate is working as you have tied VDD, and this is you are given as A. So this guy is working as an inverter. This guy is working as an inverter. The rise time is 66, the fall time is 77. They are closely matched. I will say that they are closely matched delays. Closely matched delays. Okay. So what to be done? Good enough. Okay. Any questions, doubts you have? I would be putting forward the questions and doubts, don't worry. But I thought I believe everyone is familiar with that. NAND gates are also called as universal gates, right? They are called as universal gates. And you can form any kind of Boolean expressions with NAND gates and also NOR gates, because NOR is also a universal gate. With both of the gates, you can make or perform any kind of Boolean operations, right? Okay, if that is true, then what? Then let's also make a NOR gate and see how does it works and how it is different from the NAND uncle. Let's just save this file and call it as day 1-3 gosh, man. Okay. Hmm. So in the NOR, the story goes reverse. Not much of difference, but yeah, the story is different. Just like Bollywood movies. Rich girl, poor boy, rich boy, poor girl. That's it. This is how the stories come. So you have the truth table is easy. Okay, you have 0, 0. Then what? Yeah. So this is like not of or. Okay. So for 0, 0, the value is 1. For the rest of the any input is 1, then the output is 0. Simple as that. Okay. So because this is how they are configured, they are NMOS in parallel. Okay, NMOS in parallel. So any one input turns on, the output will pull down to 0. Simple as that. And one of the PMOS will be turned off. Okay, so if this is how the schematic looks like, let's make a quick note. So again, I take the NMOS with the same width. I'm not cheating, huh? I'm not cheating. I'm just keeping the same W by L ratio parameters constant, and I get two NMOS for me, two PMOS for me, and both with same dimensions as the previous ones. And on top of each other, I just keep them and place it. Now we need NMOS in series. So I just give a VDD to one of the PMOS, VDD for the anvil, and take a metal line and short the outside nodes of the NMOS. So the NMOS will become in parallel. Then I take this guy and just bring it down. Okay, and just take the node like this, join it. Okay. Yeah. Okay. Then you take the ground and put it to the NMOS, and take the tin gate, short the gates. That's it. Okay. Now take the square clock, apply to the gate, make it 1 nanosecond low, 1 nanosecond high, redefine it as A. Take the square clock and give it to the B, make it as B, and let it be at 2 nanosecond. Automatically he increments. Then take the output node as S1, no problem. And a virtual capacitor as a token of load. That's it. We are ready to go. We just simulate this. Yeah, it works very nice. Okay, it works very neatly. So you get the rise and fall times as rise time as 125 and fall time as 40, but that's okay. And we can verify that for 0, 0, we get the output as 1. For other combination, the output is 0. Okay, so that's good. Maybe I can verify the delays by making the NOR gate as an inverter. So for doing that, I have to double click on any of the node like B and or maybe A and make it a ground. And I just go to ground tab and just say assign. Simple as that. And simulate. Now what do you notice here? Nothing. If you see that, then the A is tied. The A is tied to ground. Okay. So this guy in the NOR gate is working as an inverter. And so this is like inverter. It's not like this, right? This is not right. This is like This is grounded, and this is B, and this is how it is. Okay, this is working as an inverter. So what do you see? The rise time is 124, and the fall time is around 40. So you see, there is a gap of almost 3 times, more than 3 times, isn't it? There is a 3 times of gap. Not good enough. That's not good, because in the case of NAND, the delays were in the orders of 70s, and plus the delays were matched up already. They were closely matched up. Hardly there was a negligible difference was there. Whereas in case of NOR gate, the delays of rise and fall time, they differ more than 3 times. Okay, so they need to be closely matched. Otherwise, the design will not properly work. Okay, so that's the point 1. Okay, first of all, I will ask you guys to repeat at least the NAND gate for me. Okay, I will ask you to guys repeat the NAND gate, because NOR gate I will give you an assignment. So I'm waiting for you guys. You have to use fingers and make this NAND gate for me. And I will wait for your notification that you guys have done or not done, etc. Okay. So you have to follow through. I'm just holding up here. I just keep my video off and voice is on. Yes, guys, anyone has any doubts or questions, let me know. Is it going good? Yes, guys, how is it going? I expect this is good time to construct NAND gate. If it is taking more than this time, then definitely you. uh, Good, Akshata. That's nice. That's a good speed. That's nice. Uh, okay. Don't worry, we will get ample amount of examples, etc. Because I want you guys to practice more with trouble. Okay. Okay. So if you have made NAND gates, let me get some assignments for you guys. Okay. Okay. Good. Likit. Okay. Good. Good, Niranjan. I just give 2 more minutes for rest of the people. Good. Infant, Praveen, Niranjan got me. That's good. I was just writing the assignments. Okay, now I'm back. Okay. Okay, so if you have made NAND gate, so I just first of all give you your assignments for today, for the till you come for the next class. Now I just got a feeling that I should not be greedy in getting most of the assignments done, but yes, I want at least every one of you should attempt all these assignments. They are important, and uh, if you guys really want to scale up and level up, because I don't want this particular course to be like, assignment course where my job is just to make sure that you guys can just complete your assignment. That's it, which I don't want. Okay. In that case, then probably I would be underutilizing myself. Okay. So I would request you to be attentive and try to cover as much as assignments so that I can take you to the higher levels of the design issues. Okay. And so that you can really appreciate and enjoy this course. Okay. So you guys have to make NAND NOR gates. Okay. And you can make it kind of truth table, or in some Word file, you can just make it. Okay. And you can send me your assignments at any other places. And you have to make, first of all, 2 input NAND gate and then 2 input NOR gate. And side by side, you can put the results. And then you have to make the 4 input version of it. So the level of difference would be much more higher in case of 4 input NAND gate. Okay. And everything you have to do in 45 nanometer technology. So let it be default values. I will let you know change of technology in the next class. Okay. So with this assignments, we will talk further on NOR gate. Okay. Maybe you can right now compare NOR gate. Oh, one thing I forgot to add in this, one more line in the assignment. Make sure same order. If not, try making them. I just amended one more line in the last. You have to make sure the rise and fall delays of these gates are of the same order. If they are not, then you have to try that they are same. Okay, because this is how I want them. Okay. Now, how we will do this? May I just give you a NOR example? Okay. Then you have to decide uh, for other stuff. And remember that I will just show for the NOR gate. Okay. And when I say that rise and fall time should be of the same order, order means like, for example, one delay is 12 picosecond and second guy is 13 picosecond. So they are almost the same. The difference factor is less than 10%. So that difference is allowed. But ऐसा नहीं होना चाहिए, it should not be like this, that one guy is 12 picosecond and another guy is 40 picoseconds or 30 picoseconds or even 25 picoseconds. No, that is not allowed. Okay. They should be closely matched. Okay. So I'll just show you for the NOR gate. Okay. So for making the NOR gates of the same rise and fall time, what I do, I just make first of all an NMOS. Okay, I make an NMOS and place on the clipboard. Then before making the PMOS, as I knew that the PMOS, the delays were a little less. So I, instead of PMOS, instead of 0.2, I make the width as 0.4. Okay, and just place on the clipboard. Now, as I know that PMOS are in series, so I just take a VDD, put on the PMOS terminal, VDD for the envelope, then ground for the bottom one. Okay, then I take the 10 gates, I short the inputs, I take metal one, I just bring it, oh sorry, not this one, I just take the delete button, take metal one and bring it down and pull it out like this. Okay, then I take the square clock and apply at the gate input and make it 1 nanosecond low and high and call it A. Then I take the ground and apply to one of the input. Okay. And this is the visible node. I just want to observe what is coming over here and a token of capacitance at the output. Oh, I missed to short the NMOS from the bottom side. They are shorted now. I change color and then just I run the simulation. So here we can see that the rise and fall time delays are closely matched, but not that close enough. The fall time is 40, the rise is 55. Oh, that means the current was a little bit short of it. So I take the delete button and delete the PMOS which was constructed. And I again take a PMOS, and this time instead of 0.4, I make it 0.55 and place on the clipboard. Take the gates, join the gates back, take the metal one, short VDD for the envelope, VDD for the PMOS terminal. Change of color by pressing Ctrl W and see how it differs. So now, yes, they are closely matching. Not close enough, but yep, of the same order. So probably instead of 5.5, I should have been 0.5 or maybe 0.51, 0.2. Okay. So this is it. So this is what I have to do for NOR. For NAND, it is not required because you must have observed that for NAND gate, the rise and fall time delays are of the same order. See, the values have to be of the same order. I'm not saying that the rise and fall time of the NOR gate should match with the NAND gate. Now, making that possible is not easy job, okay? It's not required. It's just like, yes, NAND NOR should have the same order of rise and fall delays, okay? So this is what you have to perform the experiment at your places. Okay. The next time when we meet on Friday, so I should have all this NAND NOR gate made up, and we will discuss more on their power consumption properties and also other issues related to their sizing issues. I will talk about sizing, and we will also talk about the other curves of the properties what you see in the window. In the meanwhile, I'm just sharing my YouTube channel video. There's no need to like, comment, or subscribe. There's no need of doing that. It is just I'm sharing in case you miss any of the step and you want some support to see the steps involved. So during the lockdown, I made some videos and posted on the channel because of the request I got from some students. Okay, so just see if you get something of your relevance. If it's helpful to you, I would be glad of making them. Okay. So if anyone has any doubt questions, let me know, and we can discuss further on it, or we can close for the day. Yes, anyone has any doubt questions, do let me know. I just wait for a while, then we call it a day. There are few in the group. They don't write anything or talk anything. I believe Divishri, this name I'm not seeing. Dhanush, Sahana. You guys are allowed to interact, write, speak as you like. Okay. If you have any doubts, you can write me an email, or maybe I can discuss that in the next class. I just post my email ID also, my official email ID. I'm not that swift, but definitely I can reply whenever I get time. Okay. Okay. Chalo, call it a day. Okay. Thank you guys. Thanks for being here, and keep learning. Bye-bye.